Good evening. My name is Chris Carmichael. I'm the building commissioner here in Norton, Mass. I've been asked to do a presentation on the stretch code. Tonight's main takeaways are going to be defining the stretch code, what it will do for the community. I'm going to explain green communities. We're going to talk a little bit about grant money that will be available to the town. We're going to discuss what a HERS rater is, and we're going to dispel some myths about building tight buildings. A lot of FAQs on that. So again, I'm Chris Carmichael, building commissioner. To my left, I have Mike Haskell, mechanical engineer. I also have John Willard, president of Projected to Perform. Complete Energy Solutions, and I have Peter Ruiz, Projected to Perform, HERS rater. We're going to get right into a slideshow from the DORE, which will explain the benefits of the stretch community. So, as you can see, 250 now communities within the Commonwealth, as of last December, were designated green communities. That incorporates over 70% of the 360 communities and over 80% of the population. And since then, in the last few months, we've had actually several more green communities pop up. The green communities allows us to receive designations in grant programs, up to $20 million a year in grants and loans to qualifying communities. John, would you like to speak on some grant money that might be available to the town and what that could do for us?
Sure. I mean, we've done multiple projects for different towns. There's actually a bunch of different energy conservation measures you can make in your commercial town buildings, schools, such as LED lighting upgrades. You can do high efficiency boilers with hot water rebates. Not only can you get grants for these types of projects, but Mass Save has very good rebates for these types of projects. So when you combine everything together, the paybacks on them are very good. So we also do work on high efficiency air conditioning systems, energy management systems which control the buildings a lot more efficiently, has equipment running when it's supposed to be running and set back when it's not. We do a lot of Wi-Fi thermostats which can be run by the town to see what's going on within their buildings remotely. We do EC motors, which are just a new energy efficient type of motor. We also do variable speed drives for fans and pumps on your equipment, which drastically reduces their energy cost, along with high efficiency transformers, weatherization, and demand controlled ventilation, which adjusts the ventilation depending on how many people are within a building. So those are some of the projects that would typically get approved for both grant money and also Mass Save rebate money.
Excellent. Thank you, John. So we're going to go back to the slides. And this is based on Dennis's population. The grant money is based on a formula. You're guaranteed at least $125,000 plus the population and per capita income, and that there's a formula that the state applies. So we're at least guaranteed $125,000 per year. Green Communities designation and grant programs, again, the formula. And it shows you some different towns here that and how much money they have received since the stretch code and these green communities have been implemented over the last 10 years. So there's several criteria for being considered to become a green community. There's 5 criteria basically. We have to have this stretch code is one of them. So I'm going to get right into the 5 criteria on the next slide. So the first main criteria is adapting as of right for renewable energy, so wind and solar, research and development and manufacturing. We allow that as an as of right, so that means you just need a building permit, you don't need a special permit from planning or zoning. We try to reduce our energy use from the town 20% in 5 years. We adopt fuel-efficient vehicles. I'm sure everybody's been seeing the EV town cars we've already purchased. And then we minimize the life cycle cost of new construction by adopting this stretch code that we're here discussing tonight. So again, 20%, we sign up for, we do a baseline energy study and we sign up for a 20% energy reduction plan, and that's where hopefully John can help the town in the future. The criteria for the cars, the EV cars, police and fire and highway, a lot of the vehicles over 8,500 GVW will be exempt. And again, minimize the life cycle cost of the buildings by adopting the stretch code. And again, we get into the how many communities have been adopted into the stretch code already. So again, the stretch code only applies to new residential construction and new commercial construction over 100,000 square feet or 40,000 square feet for conditioned spaces like labs and supermarkets. A lot of people think that they put an addition, they remodel their kitchen, their bathroom, that they're going to have to update a lot of items in their house, and that's just not true. So this is for new construction only. It's a date stamp. If we do adopt it at the town meeting in May, we will have a concurrent period that will run from July 19, and you can go either direction, performance or prescriptive base, until January 1st of 2020, when we would go completely performance-based and have to hire a HERS rater for the stretch code. So 10 years ago, when the stretch code was first adopted by a handful of communities, the stretch code was a 40 to 50% savings. It was a higher energy. You'd save a lot more. But the International Energy Conservation Code has become much more restrictive in the last 10 years. So the stretch code is not so much longer of a stretch. There's probably only a 5 to 10% difference now between what the stretch code was when we were building with 2x4 walls with R13 and R15, as we were discussing prior to going on camera, to the R20 that's required on the walls now, and the R49 in the ceilings when it was only R19 maybe 10 years ago. So there's much more. It's much more stricter, the codes now. So to go from prescriptive to the performance-based isn't much different from what we're requiring already. The major difference between the base code and the stretch code are we take away the prescriptive formulas, which are R20 in the walls, R30 in the floors, and R49 in the ceiling, and we go to a performance-based system where we're required to hire a HERS rater, basically a design professional that's going to help you design the house. Peter, do you want to kick in at this moment and speak a little bit on that?
Well, one of the things that we do in the HERS process is before the home is even permitted, we get involved, we take a look at the builder's plans, and we try to interject some ideas of how to do things as efficiently as possible with the most minimal cost impact to the project. There are a lot of things you can do in a home that make it more energy efficient. You can also throw a lot of money at a home, but it doesn't make it more energy efficient. But throughout the whole process of building the home, through extra inspections, through specialized tests, and through the certification process, we help design a home that meets the stretch code process.
Excellent. Thank you, Peter. So again, why test performance? As Peter just discussed, prescriptive codes don't really guarantee a good installation. You have air leaks and water tightness, so thermal insulation can be ineffective. Small air gaps can reduce the insulation, the R values by 50% or more. So that's why HERS raters provide a third-party verification that this project is being built properly. Again, the HERS process, as Peter just discussed, reviewing building plans, second inspection. I'll be still inspecting, but Peter will go out there during construction as well. And then a final blower door test. You do the ductwork as well, correct, Peter?
Yep.
Ductwork and the whole house fan.
Yeah, we test the ductwork for two different tests. We test it for duct tightness, which is the quality of the install, and then we also test it for leakage to the outdoors, which shows how much of that duct leakage is actually leaving your home, and that's the most important spec. And then we combine that with the blower door, and all of those pieces together are added to the formula to see your house's energy efficiency.
Excellent, excellent. Again, in-process inspections. What is the HERS rating system? Peter, can you see this slide?
Yep.
All right. So the annual energy analysis, heating, cooling, water, heating, lighting, and appliances. And they base it on a model home from the 2006 code, and then so that was based at 100, and now we have to meet this 55, is that correct?
Yeah, so what they estimate is that if you build at base code, you'll be at about an 80% home. When you build a stretch code, you pull into a tighter home, but it's not necessarily that you're building any differently than you were. You're testing and you're perfecting the home. So most of the time it's the same R values in the home, the same type of equipment. It's just done to perfection.
It's excellent. Well, I'm seeing that on commercial projects right now. They're building a passive house design at Wheaton College, and the contractors actually have a blower door in their trailer, and they're testing each portion of the building as they're going and ensuring how tight it is. So it's changed a lot in construction in the last 20 years because of this. So again, this is the end of the stretch code presentation from the DORE. And I'm going to introduce Mike, and Mike's a mechanical engineer. And while I get his slideshow up and going, do you want to talk a little bit about that while I get you up?
Sure. Yep. So I do have an engineering background, but I'm a homeowner here in Norton, and I just finished my own personal single-family house for my family here in town, and went through the entire building process with an eye towards the energy efficiency of the new house build. And what I'm going to be talking about, the performance of our house, we actually went past the stretch code, which Chris mentioned isn't much of a stretch anymore. We went past the stretch code to actually design and build a net zero house. So if we think about the HERS rating scale that we just saw, 100 being a baseline house from 2006, somewhere in the 80s to 50s would be a new stretch energy code built house. A net zero house would actually score a 0 on that scale. And what that means simply is that the house itself, it generates all the electricity that it needs for heating, cooling, ventilation, and electrical plug loads for your appliances and that sort of thing. So the idea is that the house is kind of self-sustaining and sustains itself over its lifetime without using fossil fuels or any other additional energy sources. So I have a small presentation here just going over the house from a high level to explain the process we went through with the design, and really as an example what the design, how it differs from a code built house, and then really what the benefits are to the homeowner over the life of the process. So as I just mentioned, a net zero house, really the key is that it produces all the energy on site in renewable fashion that the house will need on a year-to-year basis. So it would cover all heating, cooling, electrical plug loads, hot water, and appliances as well. Here in New England, obviously, our electrical loads in the house are much higher in the winter as we need heating, and the solar output is a little bit lower in the winter. So net zero really is year to year. We sum all of our usage and our production, and it zeroes out at the end of the year.
So if I can just interject at this point, we're not going to achieve net zero with the stretch code.
Correct.
Mike has far exceeded the code by going towards a net zero house, but he's had such wonderful results. I had to have him come and speak tonight, so I'm sorry to interrupt.
And absolutely, and the stretch code is something that, again, the point is it's not really much of a stretch. It's not a huge deviation from what we're currently doing. And in fact, going much further than a stretch code is extremely possible in Norton with little to no financial impact up front. And certainly over the long haul, it's a great benefit. So financially, this is, I think, the major question for a lot of homeowners is what's the cost to go net zero? What do you have to invest up front? How long is the payback period? And, having just went through this with the past year, we've been in the house about 9 months now, you can make a really strong case that by designing the house correctly up front and making some smart choices on energy efficiency, you can actually build a net zero house for nearly the same cost from the start as a typical code built house would be. And then of course from day one on, once you move in, the lack of any sort of utility bills or electrical bills really makes it extremely attractive, in addition to home comfort, which is really indoor air quality, something we'll talk about here on the next slide. So in summary, the house is a really typical colonial 4-bedroom, 3-bath house. And you can see on the front facing, which again is a south-facing roof, is a solar installation. Currently, we have a really nice surplus going that'll just build throughout the rest of the summer, and we're projected to finish year over year with about 3,700 kilowatts of a surplus. So put that in perspective, that's roughly $700 or $800 of actually surplus balance on your electric bill at the end of the year. But it's just a typical colonial house, doesn't look any different than any other house would be. It's just some extra care and steps we're taking during the building approach. So overall, we looked at the house design really from an efficiency standpoint. Things like walls were built out of 2x10s instead of typical 2x6 construction. We used a flash and bat approach to increase the thermal efficiency of the wall without paying a huge price penalty. So we had all the advantages of using foam insulation, but not really paying for the full wall cavity being filled with foam. We offset that with fiberglass as well. The extra cost and labor that went into actually building those walls is offset by the reduction in cost on the mechanical side. So instead of having, say, an oil furnace, oil tank, chimney, forced hot air, or baseboard heating, all of that is replaced with simple mini splits that are mounted throughout the house, provide spot heating and cooling to keep the whole house comfortable. So a little bit more money invested in the envelope of the house was offset by a greatly reduced mechanical cost in terms of heating and cooling for the entire house. So that's really the key to get net zero performance without a price penalty from day one. Of course, everything after day one is a great financial benefit to the homeowners. So I don't want to get into this too detailed, but this is some of the things we talk about, the Curtis Raters specifically we talk about, which is the heat loss calculations in the house and really trying to design the house for most performance while still being financially reasonable. It's easy to throw a lot of money at, say, fancy windows or spray foam, things like that. But as a homeowner, I really wanted to understand if it made sense financially for me to go through. So these are just some calculations which allowed us to size the HVAC system in the house. Again, the wall design is a little bit different than you would find in a normal house, but not drastically so. It's still a single stud wall. Nothing too out of the ordinary there, except it is a 2x10 thickness. So we have much thicker insulation with a fiberglass and spray foam combination within that wall. So we're roughly R38 in the wall, but very airtight, which is critical.
Now, if I can interrupt again, and I apologize.
No.
I'm hearing different things, and Peter, please help me out. I'm hearing about controlling the dew point within the wall and putting insulation on the exterior of the wall to control that dew point so you don't have the moisture build up inside. Did you consider that when you looked at the 2x10s? Or?
We did, yeah.
Okay.
So the important thing is you don't want the dew point to be on a cold surface within the wall to avoid condensation. So by putting the spray foam on the inside of the wall, we made sure that it was always kept above the dew point as well. So.
Excellent. So that's critical, and that's why we again hire people like Peter at the beginning to control that moisture level within the wall cavity. And we'll be talking further about that in mechanical.
Yeah, and so these are the mini split heat pumps that we used in our house, and actually it turned out great. We used 4 of these to heat and cool the entire house, and actually one of the 4 we haven't ever had to turn on. So essentially, we've really only used 3, even throughout this winter when we got to about 0 outside. It performed great. So not only is it very comfortable in the house, extremely efficient, there's also really nice incentives that Massachusetts has for these high efficiency appliances within the house, really offset the cost. And again, bring the entire sum of the project cost right back in line with a typical code-built house would be. So one thing that we need to kind of understand as we go through this house build and we try to make everything as tight and as efficient as possible is, of course, indoor air quality for the occupants. So what we used in my house is an ERV, energy recovery ventilator. What we're basically doing is bringing fresh air into the house at certain points, into, say, the bedroom, living room, kitchen area, and pulling exhaust out of bathrooms and near the stove areas in the house as well. So this is a constant refreshing of air within the house to keep humidity, dust, CO2 levels, all really within the optimal point. The difference with an ERV versus a simple, bathroom fan is that we're actually recovering the heat that we just paid for coming out of the mini splits. Instead of pumping it all outside, we're actually recovering that heat while still having fresh air. So it's kind of the best of both worlds, where indoor air quality is high and also efficiency and thermal performance is also high. So this is something that, again, it's an extra step of design. Really working where your ventilation points are going to be within the house has to get done kind of during construction to be the most optimal. But from day one on, it's really a really benefit to the homeowner itself, and something that I think is a good path going forward.
How much is a unit like this, Mike, an ERV or an HRV?
Yeah, so this is a Panasonic model, really high quality, high performance, and it's just about $900 for the setup. Installation and ductwork would vary depending on your application, but overall pretty reasonable for the comfort and for the health of the occupants.
So less than half of 1% of the total cost of construction, would you say?
Yeah, absolutely.
Oh, well worth it then.
Absolutely. Yeah. This is the solar array on the house. Again, a lot of thought was put into the house's orientation on the lot, shading from trees, that sort of thing, to really optimize it. But the big thing here, takeaway, is of course its performance electrically, but financially, Mass, because of their incentive programs, the SREC program, the solar array was actually a net positive income from day one. The SREC payments were actually larger than the finance cost of the solar system. So from our first month, the system was paying for itself with the added bonus of free electricity coming off it with no electric bill. So it was really worked out great. And again, so another one of those incentives that Mass really tries to get homeowners and its citizens to take advantage of. So we've had great luck with the system. The house as a whole, because we designed it as a system, is performing great. And overall, even though its performance is quite a bit past the stretch code requirements, it wasn't really that much more difficult or costly to do. I think that's probably the last slide to go over, but
That's great.
overall, it's been a great experience here in Norton, as a homeowner, and I'm going to be happier with the results that we had.
Excellent. So we just have a couple more slides, and I wanted to conclude tonight's meeting talking about a few more things, mostly FAQs on indoor air quality. So if I can just take a second and get these up. So the new Mass Stretch Code, again, this is what we're hoping to adopt at the May town meeting, is section AA 103.1 of 780 CMR, so that we'd be adopting the stretch code, basically. So this was this energy use was based on the 2012 IEC. We're on the 2015. So you can see at the bottom there's about a 13% difference between what the stretch code and that 2012 is. We're in the 2015 now, and it's probably between 5 and 7% difference.
Yeah.
Peter? Yeah. So again, it's not much of a stretch code anymore. So we're able to get in on this program at the 12th hour and still get money for the community. So this is a win-win situation. Compliance paths. So basically, there are 2 compliance paths that we can go with. Right now, we're doing the prescriptive-based path and just using whatever's written in the code. Again, R30 in the floors, R20 in the walls, and R49 in the ceilings. If we go to the stretch code, we're going to be using a performance-based path, and we're going to be hiring HERS raters. Peter, again, do you want to kick in at this point?
Yep, I actually do about 150 HERS ratings in Massachusetts now. A lot of them are in non-stretch code communities, because the builders have figured out that their buyers want to buy stretch code community homes. They want to buy homes that they know how much it's going to cost to heat, how much it's going to cost to cool. And the other piece to that, between the free light bulbs from Mass Saves, the rebates from Mass Saves, most of them comes most of the time the HERS rating comes at very little cost to the builder, but he already had to pay for those tests. So now the tests are almost free. So it works out to be a benefit for everybody. And now MLS listings online have a spot for the HERS rating to plug in, and you can actually search online at what the HERS ratings are in the town.
Excellent. So the educated consumer is driving this.
Yeah.
And over the life of the loan of the house, the 30-year mortgage, you see an exponential return on these homes, don't you?
And if you see someone going online who is a smart or a knowledgeable buyer, and they add that filter looking for the HERS rating, they're not going to see your home if you're not HERS rated.
Excellent. So this is, again, a win-win situation. And again, we're going to just take a couple of minutes and talk about mechanical ventilation and the hows and whys of building a tighter home and why we want to ventilate it properly. So again, the HERS Rater's motto is build it tight, ventilate it right.
Yep.
So we're going to talk a little bit about the three different types of mechanical ventilation. Basically, mechanical ventilation, well, first of all, we're going to talk about building as a system now. We're not building just boxes that we're living in and with a fireplace anymore. We're building a system. The exterior is keeping the water and the rain and the vapor out. We have air movement. We have to the enclosure has to control the heat loss, the heat gain. We have to consider the heating, cooling equipment, mechanical ventilation, plumbing, electrical, you name it. So we really are building systems now. So that's why it's so imperative to hire a design professional at the beginning of the project, not just leave it on Bob the Builder, who might want to cut a few corners. So not that I know any of those guys. So why ventilate? Again, Mike discussed this earlier when he talked about ventilating. We want to rid the house of moisture from its inhabitants. When we breathe out, we exhale moisture. When we bathe, we cook, we produce moisture in the house. Hot latent air from in the house needs to be ventilated. Breathing carbon dioxide, nitrogen dioxide, the tobacco, you name it, it's in there. We need to get it out. Otherwise, we're going to have a sick building syndrome. Uncontrolled ventilation, basically what we're seeing in just prescriptive homes right now is unreliable. It's just basically controlled by the wind and temperature differences, and you have no occupant control.
One of the things here that a lot of people don't realize is this is also, you're relying on stack effect, which is similar to how a chimney works. You get the chimney warm, creates a vacuum and pulls air up, which is also why most homes that are in the town currently, your first floor windows will appear to be leaking more than your second floor windows, and it's because the air is being pulled in the home at the bottom floor, and now you've got the high moisture content air heating the air from your home. You get your condensation, and then on your second floor your windows look fine, but realistically the air up top is leaving the house. So your natural air changes per hour are uncontrolled, and they're typically higher than 4 to 5 air changes an hour in an older home. When you add a mechanical ventilation system, any type, balanced, ERV, pressurized, you change that stack effect. And what that does is it controls the ventilation of the home. So instead of having an uncontrolled 400 or 500 CFM leak, you have a controlled 40 CFM leak. So you can take an existing home, add a ventilation project to it, and you can actually make the house more energy efficient just by ventilating it correctly, because now you're not having uncontrolled air changes per hour. You're not having to heat air outside of your normal cycles. And then the indoor air quality, humidity, everything starts to become under control, and the home starts to actually perform better.
Yeah. So again, that stack effect is creating that uprise of air, and it's pulling air in through the bottom windows, and it's also coming from the crawl spaces in our basement.
Anywhere.
So, right. So that moisture-laden air or dirt is coming right into the house. That's why we want to ventilate. So controlled ventilation, mechanical ventilation. Again, there's 3 types. We can control it. The occupant can control it, and as Peter just discussed, we can filter it, we can temper it, and we can build the houses a lot tighter because of this. So again, build tight, ventilate right. So there's 3 main ways that we, compliance method, Energy Stars, ASHRAE, or Mass Formula.
So each one of those formulas basically takes into account your designed air change an hour of the home, then your at the end, your final test, your actual air leakage per home. That calculates into a lengthy formula that's based on how many bedrooms, how many square foot, how much glass area you have in the home, and that gives us the ventilation requirement that is recommended by whichever one of these formulas.
So you do all those calculations at the end, and then you tell them how long the fan's going to be ventilating for.
And then we set it. We actually set it while we're on site, and we certify it before we leave. And we add non-tamper stickers to them because they're supposed to be a set and tested device.
Excellent. So again, the ventilation airflow rate that Peter was just discussing is discussed here in this slide. So the house size, the number of bedrooms, the height of the walls, the air leakage, and the location is all discussed, all calculated at the end.
Yep.
So again, the three main types of ventilation are exhaust only, which creates a negative pressure, a supply only, which creates a positive pressure, or what Michael did in his house, balanced ventilation, which I'm leaning towards. But again, there's all three paths are code compliant. So exhaust only again creates a negative pressure throughout the house, typically done through a bath or a combination house fan, and the pros and cons of this are on the next slide. Well, here's Peter's controller that he sets on the fan. No tamper sticker. This is basically the most simplest and the most common, right? Because it's the least expensive.
And it is functional. By design now, home windows are designed to leak a specific amount, and they've actually added filters to the edges of the window. So if you look at a new window and you tilt in the sash and you look at the gaskets on them, they're actually now small filters.
Like a HEPA filter.
Like a HEPA filter. They have about, I think they say around 20 to 30 years worth of capacity if you
Wow.
count up all your windows. And by having them on all of your new homes, when you create that slight amount of negative pressure with that mechanical fan, you now pull air in from every window instead of just one or two. So now you have fresh air over the whole home. It's a different technique. It's not the most ideal. Balanced would be ideal. But price-wise, it's about $12 a year to run that fan 24 hours a day, 7 days a week. And it gives you fresh oxygen in the home 24 hours a day, 7 days a week. Unlike natural ventilation, which you get more ventilation on windy days, almost no ventilation on a wet day, and excess ventilation on a real windy day.
Excellent. Excellent. Thanks, Peter. So the advantage of exhaust only is, as Peter was just discussing, it's easy to install, it's simple, it's inexpensive, and it reduces the moisture loading of the walls assemblies, which is critical. We want to
really good point to this is I can say in the last 3 years I've had about 12 customers call and say that they have moisture that's forming on their windows, and before I even go on site I just remind them, I know you could read online how to turn the fan on and off. Turn the fan back on and I'll be out in 2 or 3 days to check it. And they never have me come back out. That fan those formulas are fairly precise. If you keep the system functioning, the home as a system functioning, you keep that moisture under control.
I get similar phone calls from new homeowners complaining about the bath fan and the hows and whys of it. And I try to explain this to them, but they still shut it off.
If they use the right bath fan, by design, it's supposed to be less than 0.2 sones. You shouldn't hear it, even at full speed. If you hear it, most likely it was not installed 100% correct, which is where guys like me come in. We check those things when we're...
The Panasonic fans are whisper quiet.
Oh, yeah.
And then there's remote fans that they can be installed in the attic.
Oh, yeah.
So there are ways around it.
Yep.
So the disadvantage of an exhaust-only system, again, is this creates a negative pressure within the air. The makeup air takes the path of least resistance, so it's coming through the windows. We try to have it come through the windows, but it's still coming through the basement and the crawl spaces.
If they're not sealed correctly, yes.
And I've heard horror stories of too much negative ventilation causing problems with combustion appliances and gas appliances.
And that brings up a really good point. One of the big things I see in this area when I do surveys of homes is that they have combustion appliances inside of the building envelope, which should never happen. And it's not caught in an environment where it's not checked by specialists. And it's been done this way forever. So a lot of times people have seen it for so long that they almost gloss over it because they almost accept it as what it is.
Yeah.
Naturally drafting devices in a home that's built correctly, even to IECC standards, should not be within the building envelope without designed ventilation for them.
Again, we go right back to the basic need to have a design professional brought into to the building prior to its construction.
Yep.
Just like you do and Mike did in his house.
Yeah.
So we're going to get into the next type of ventilation is supply only, which creates a positive pressure within the house. And again, this is another method. I'm sure we're not seeing I don't see too much of this. Do you see some of it?
Where we see this a lot is used as makeup air. when you have an over 400 CFM exhaust, or you have multiple washers and dryers, and you may be running 2 or 3 dryers at the same time. There are a lot of homes that still do that. And when the house has negative pressure, there's a sensor on the device where it says the air control damper. There'll be a pressure sensor on that, and it only allows in air when there's a need for that air, and then it closes it off. That way you're not pulling cold, unfiltered air into your system often.
Excellent. Thank you, Peter.
Yep.
So again, the advantage of the supply side does not interfere with the combustion appliances that we were just discussing. And it is a better distribution of the fresh air. The disadvantages does not remove the air pollutants because we're not exhausting. It brings in colder, hotter, or moist air from outside. The air circulation can feel drafty. The furnace fan runs more often. And then this is my biggest pet peeve with this, is that the interior air, the hot laden moisture air, is pushed into the cracks in the assemblies of the walls, causing moisture and mold and mildew. So that's the biggest disadvantage of the supply side. The last ventilation type, or mechanical ventilation, is balanced, like Mike put in his house. So Mike, please feel free to kick in on this.
Sure. Yeah, so the advantage of the balanced ventilation is that you can take air out of the house exactly where you want to and bring fresh air where it's most needed. So places like bedrooms at night, you can bring fresh air into the bedrooms at night. You can pull air out of places like bathrooms, kitchens, where there's high moisture content. So not only can you kind of put spot solutions in your house where you need fresh air and need to pull out exhaust, the balanced ventilation is the only method to actually recover the heat or the air conditioning that you just put into your house. So in the summer, you have hot, moist air outside. It runs through the ERV. It releases some of its moisture to the outgoing stream. So the air that's coming into your house is actually cooled and dried compared to what is outside the envelope. In the winter, obviously, very important in New England, just the opposite happens. The cold air comes in, it's pre-warmed by the outgoing air. So instead of dumping, say, 20-degree Fahrenheit air into a bedroom, it comes in tempered nicely, maybe 62, 63 degrees, and mixes really nicely. So it's not really a cold draft coming in or very dry air. In the winter right now, dry air is a big complaint for colds. People get sick, get cold, and they put a humidifier in. And the last thing you want to do is just keep pumping in dry, cold air into your house when you spent time and money to actually humidify that space. So balanced ventilation, I think, is a great method to go, but certainly it's more costly. It's harder to put in, and it really should be done at the construction or renovation phase. It's a little tougher to kind of retrofit unless you have existing ductwork that you can kind of modify.
So all the calculations are done, how much we're ventilating and how much we're taking in. And again, that intake air or makeup air is being brought through that manifold, and you're exchanging or tempering the air before we put it into the furnace, creating less BTUs to heat or cool that in the heating or cooling months.
Exactly. Yep. It's the fan draw is one part of it. So you kind of figure out how much does that fan cost, as Peter was saying. But the other thing is the other cost is conditioned air that you're now putting outside. So if you don't have an ERV or an HRV and you have a fan only, you also pay a financial penalty on that air that you heated or cooled that you're now pumping outside. So they are more to buy up front, certainly, and install, but there's certainly a payback over a certain amount of time where you're saving on your utility bills.
Yes.
As well. So,
Excellent.
and of course, the filtering is nice. They have MERV 12 or MERV 13 filters, almost a HEPA type filter within the ERVs to filter the air.
So again, this slide shows the breakdown of the HRV or the ERV, and again, the heat recovery unit is the same as the energy recovery unit, but then you have on the energy you have a moisture control aspect of it. Is that correct?
It is, yeah.
So I'm hearing negative things. The only negative thing I hear about this, and it's small, is that the condensation or the moisture being trapped in that might freeze in really cold weather. Have you experienced that? Or?
Yeah, so the ERVs that have a little bit more intelligence actually have temperature sensors built in. So if the fan's running 100% speed 100% of the time during normal operation, if it is extremely cold out, 5-10 degrees Fahrenheit, some systems, mine in particular, will only run, say, 40% of the time.
Gotcha.
So it won't actually freeze the core, the filtering core that's in here. It's really specific to which ERV or HRV you
So
select.
these systems have evolved even in the last 5 or 6 years since they first come onto the market.
Yeah, absolutely.
Excellent.
And there's also another aspect to that, again, comes with knowledge. They're designed to be installed in a temperate zone. A lot of times it's
Inside the
convenient to
building
stick them
cavity,
in a
yeah.
basement,
Yep.
and the basement is cold. The whole idea is the energy recovery happens by that box being at the temperature of the air in your house. So if that metal cavity is cold, it's going to take on cold a lot quicker. So again, it all goes back to learning the building science and understanding all of these devices.
Excellent, excellent. So last couple slides and then we'll end this. The advantage of the balanced ventilation is the makeup air is the pathway is known. So we're bringing in, we're tempering it. The distribution is known. We filter the air. We cover the heat and the cool and the moisture as just discussed. No induced infiltration. The disadvantages, basically only the cost and the complexity of the system. But again, these have evolved as just discussed. So again, mechanical ventilation is required. It's part of the code. There are 3 different types, but I just wanted to dispel some myths tonight about that. So again, we're going to end with Peter. Did you have something to add?
Yeah, there's one other piece to this. The ERVs also have a dedicated rebate, so to help compensate for that. So it may take away $200 or $300 off the cost of that device.
Excellent.
And they are typically about a 3-point credit in your HERS rating. So if you have too much glass, sometimes you can make up for it by adding an ERV. It's all about, the whole idea of stretch
Trade-off.
code is to stretch the code. You're allowed to give and take.
Some
If
trade-offs. Sure.
Out of the 150 homes or so that we do a year, I probably only do about 5 that have anything more than fiberglass and blown cellulose in the attic. Spray foam is an oddity. It's not needed everywhere. I have some customers that swear by it because their customers swear by it. But a conventional 2x6 home, fiberglass in the wall, blown R49 cellulose in the attic, and conventional fiberglass in the floor will oftentimes pass the stretch code without a problem. You just have to do your equipment correctly.
Excellent.
And
And
one
again,
of the biggest things that they've started to do is they've started to really push that you need to understand your mechanical equipment before you start building your home. So you need to know that you're sizing it correct. A lot of mechanical vendors that sell equipment now, you can't even justify having 2 heating systems in a home anymore. Because unless the home's over 2,800 square foot, most of the systems are designed to run that as a single system. So you'll be hard pressed to see systems in the attic and in the basement serving a home anymore because you don't need that much heat anymore.
No, it brings me to a point. I had a plumbing inspector that's been with us for 40 years almost, and he was shocked and amazed at the size of the units going into these new houses. Where he thought it would be a 4-ton unit, it's a 1.5 ton or 2 ton.
Yeah.
So it's a sign of the times. So I'm going to end on Peter's motto: build it tight, ventilate it right. And I'd like to thank everybody for joining us here tonight on a presentation of the stretch code, and I hope you support this at the Maytown meeting. Thank you and good night.